Section 3 was about waves. In this section, we are going to define the waves. We will start defining the water waves first. As you see, surface of the water is flat. There is no vibration on the surface of the water. But if you drop a piece of rock onto the surface of the water, you are going to see that the surface starts to vibrate up and down. And this is called in physics disturbance. Yeah, it was normally flat, there is nothing. But when you drop a pebble onto the surface, you disturb the water. And it starts to be vibrating. The disturbance starts from the point the pebble hits, and where you hit. From this point, disturbance starts and expands, becomes larger and larger in all directions. Later we learn that the speed of a wave depends on medium. So all around, medium is water. That's why every disturbance on the right, on the left, forward, backward, cross, on the right, cross, left, all travel with the same speed. That's why disturbance expands in all directions with a circular pattern. Reason is that otherwise, if they were traveling in different speeds, it could not be a circular pattern. It's a circle because every point disturbance travels with the same speed in all directions. That's why we are going to observe that this disturbance is expanding in circular wave pattern. This traveling disturbance is given a name in physics, which is called a wave. Yani, short definition of a wave is a traveling disturbance. As this water wave travels, something surprising happens. If you drop a small ball onto the surface of the water, you are going to observe that this ball is making circular paths in vertical circles. And after one cycle of vibration, its net displacement is going to be zero. In fact, we know it in this circular motion and simple harmonic motion as well. So in simple harmonic motion, we know that after one cycle of vibration, net displacement is zero. In here also the same thing happens. As this particle completes one cycle of vibration, up, down, right, left, its net displacement is going to be zero. That's why as a wave is passing by an object may vibrate up and down, may vibrate back and forth, but its net displacement after one cycle is going to be zero. Yani, waves move from one place to another, but the water, particles of the medium, is not carried with it at the outside. So waves are moving from right to left, but the leaves are only moving up and down. Net displacement is zero. This is what wave is in physics. If a disturbance causes a particle to displace from one point to another, it's not wave in physics. It's called flow, like river. River carries an object from one plate, one position to another position. So we don't say in physics it's a wave. It's called a flow. A wave does not carry. It only vibrates back and forth, up and down. After one cycle of vibration, net displacement is zero. This is in circular harmonic motion. We talk about this. And yes, medium waves need or disturbance to disturb some medium or some place. You need a medium and particles like water. But every wave does not need a medium to travel. Only mechanical waves need a medium. So what is medium? The material through which disturbance travels is called medium. My sound now arrives in your ear, so we need a medium. Air molecules are the medium. Air is the medium. So by this way, my sound can reach you. If I try to talk to you in free space, you cannot hear me because there's no medium. So mechanical waves need a medium. Water waves need water. Sound waves needs air. Earthquake waves needs earth crust. spring we did in the experimental lesson, remember, when there was a disturbing spring, it needs coils to travel. But electromagnetic waves do not need a medium. Light is the best example. From sun to the earth, there is no medium, there is no molecule. How light is coming? Because they are electromagnetic waves, they don't need a medium. Not only light, radio waves, ultraviolet rays, infrared rays, so all electromagnetic waves, none of them needs a medium, even they are fastest, if no medium. In free space, they are fastest. When they enter to a medium, they slow down. In water, in glass, light is slower than the space. So according to need of the medium, we classify the waves into two groups, mechanical waves and electromagnetic waves. And electromagnetic light traveling with speed of light. Mechanical waves depends on the speed. Later we will talk about the medium, how fast they travel. And now we are going to continue types of waves. Or define a wave, pulse wave. How can we produce a pulse? You are going to flip one end of a tall drop up, then back down to where you started. Yeah, if you start from here, up and back here, so this is producing a pulse. This is a pulse. Look at the hand. This hand completes how many cycles? How many? Half cycle. Then can you say that half cycle produces a pulse? Can you say that? Yes, if you vibrate one end of a half cycle, you are going to produce a pulse. If you continue full cycle, two pulses. Yeah, if you do like this, once again, down there, and back again, you are going to produce one pulse down. Altogether, this is a complete wave. Yeah, a complete wave is done by two pulses. Each pulse is produced by a half cycle above the equilibrium position, half cycle below equilibrium position, one complete cycle, one complete wave. If you repeatedly move your hand up and down, of course you are going to produce several complete waves one after another, which is called periodic wave. Yeah, and moving one end of a tall drop up and down repeatedly, repeated motion in physics is called what? Periodic motion. So you are going to produce periodic wave, just like this example. So this hand is moving up and down repeatedly, and on the drop you are going to produce periodic waves. A very important statement. Every wave carries the property of its own source. Like what? This vibrating blade, remember it was the ruler elastic object. There's a rope attached to this vibrating blade. As blade is vibrating up and down, of course, particles of the rope also will be vibrating up and down. So a blade vibrating up and down produces a wave on the string, and blade, elastic object. If elastic objects are vibrating, they are vibrating with simple harmonic motion. Remember mass system. So the source is the blade. If the source is vibrating with simple harmonic motion, every single point on the rope also vibrates with simple harmonic motion. The vibration of each point on the string is also simple harmonic. Yani source characteristic and wave characteristics are almost same. So if the source is vibrating simple harmonic motion, so the particles of the medium vibrates with the simple harmonic motion. In this case, pattern of the wave is going to be similar or exactly the same as the sine function. So look at that. It is very similar to a sine function. That's why these waves are called sine waves, because of the similarity between the pattern of the wave and graph of a sine function. This was the definition. If the source is vibrating with simple harmonic motion, every particles of the medium vibrates with simple harmonic motion. That's why wave pattern is going to be sine wave. And when we do this experiment in the classroom, you saw that, remember the tissue, tissue only vibrate when as the wave is traveling from right to left. Yani this point, and you choose one point, this point initially at equilibrium position, later vibrates to in here to the top, then back to equilibrium position, then down. Yani particles are vibrating up and down while the wave is traveling from left to right. And these waves are called transverse waves. Yani as wave is traveling in horizontal, but the particles are vibrating in vertical. Angle between direction of the wave motion and particles vibration is 90 degrees. These waves are called transverse waves. The example. So the wave is traveling in horizontal, but the coils are vibrating in vertical, so angle between them is 90 degree transverse waves. Wave on drop is an example. Or all electromagnetic waves. Yani we don't study electromagnetic waves in detail, but let you know this. Electromagnetic waves are transverse waves. They of course they don't know medium, but they are vibrating, not medium, something else is vibrating. This vibrating thing is called electric field. We know it. Magnetic electric field are continuously vibrating. So they are also vibrating perpendicular to the motion. That's why these electromagnetic waves are transverse waves. But second type of wave which we can observe is longitudinal wave. In here, particles vibrate parallel to wave motion. Yani, if I ask you, what is the angle between direction of vibration of the coils and the wave motion? 0 or 180. But in here, 90. And until now, no questions like this, but why not? Why not? Okay. Best example for longitudinal wave is sound. We will study in chapter 4 in details the sound. And or when you pump the spring like this, you produce vibration horizontal, wave motion is horizontal too. And of course we should study waves in details. To study waves in details, we have to put the waves in a coordinate system. We can put a transverse wave to a coordinate system, or we can put a longitudinal wave in coordinate system. This representation is called waveform. Then I am going to take this wave, which is a wave on a rope, put it, locate on the coordinate system. So this is called a waveform. Representing a wave in a coordinate system is called waveform. Both transverse and longitudinal waves can be represented in coordinate system. This is what the transverse wave is. One of them is waveform that represents the displacement of each point at the wave of the wave at single moment. Yani, when there is a wave traveling in a rope, you are going to take a picture just once. Some points are at negative maximum, some are at positive maximum, some are at equilibrium. It's different, particles are different positions. When you combine them all, it's the wave. Then picture just one distance. But there is one more waveform told in your book, but it's not going to be studied. You are going to just watch one single point at time. Sometimes it's at equilibrium, sometimes it's at maximum, later, negative equilibrium and negative maximum. And if you single wave at different times, it's also a waveform. But just these definitions given in your book, no other descriptions are done. Yani we are going to study this waveform. Yani you are going to take the picture of a wave at an instant. Different points are different positions with respect to the equilibrium position. Then we are going to study this way. So, first we are going to define points. When we take a picture of a wave at an instant, some points will be seen that at highest displacement from equilibrium position, farthest displacement. Farther displacement above the equilibrium position is called crest. Point. Also, maybe you remember in chapter 3, section 4, this is defined as maximum displacement point in one of the questions. They define that. maximum displacement point above the equilibrium position is crest. Maximum displacement point below the equilibrium position is trough. So highest point above the equilibrium position is called crest. Lowest point below the equilibrium position is called trough of this wave. Also we have equilibrium position. And equilibrium position here, crest, equilibrium, trough. 2 points. We can measure the wave in horizontal and also in vertical too. Now we are going to define the length. In vertical, distance from equilibrium position to a crest, which is maximum displacement point. From equilibrium position to a trough, another maximum displacement point on the other side. This distance is called amplitude. Yani above the equilibrium and below the equilibrium, these distances are amplitude. A and A. The distance from equilibrium position to a crest to a trough is called the amplitude. Okay, let me ask a question to you. If this distance is given to you, 20 centimeter, what is amplitude? 10. 10 plus 10, 20. And one of the questions will be this way. Then sometimes I see that some students are just directly writing this number. No, this number is twice of the A. A plus A, 2A is 20. A is 10 centimeter. 10 plus 10, 20.
So hocam, the 20 centimeter is for like equals to the magnitude of a complete cycle?
No, 20 centimeter is the distance from a half cycle. From one maximum displacement to other maximum displacement, it's half cycle. Do you remember that? So from maximum displacement to another and back again is one cycle, and distance traveled in one cycle was 4A.
Right.
Distance for half cycle is 2A, yeah? This is 2A. 2A is 20 centimeter, A is 10 centimeters. And we are going to also measure the wave in horizontal, which is called wavelength. So, distance between neighboring displacement is called wavelength. Neighboring displacement. What does neighboring mean? From one crest to next crest. From one trough to next trough. This length is called wavelength. Distance between two adjacent similar points of the wave, such as from crest to crest or trough to trough, is called a wavelength, lambda. But this is not only wavelength. Also, length of a complete wave. What is complete wave? We learned it at the beginning. There must be one pulse up, one pulse down. This is a complete wave. So, from here to here, also one lambda. One complete wave. Length of a complete wave is one lambda. From here to here, also one lambda. So, can you conclude that from one crest to next crest, there is a one complete wave? Can you say that? Yes, we can. From one crest to next crest, there is a one complete wave. Or from one trough to next trough, one complete wave? Yes, we can. It is one lambda. Yani, if you measure one lambda distance on a wave, between those points, absolutely you have one complete wave. It is also the distance the wave travels during one cycle of vibration of any point on the rope. We just learned that half cycle produces one pulse. Another half cycle produces one more pulse. Two pulses together, one wavelength. Yani, if you vibrate your hands, or the source vibrates once, one cycle, this source produces one lambda, one wave. Two cycle produces two waves. Three cycles of vibration produces three waves. Of course, to produce those waves, they must travel. And that's why we say that in one cycle, when the source is completing one cycle of vibration, the wave on the medium travels one lambda distance. Now this is all about transverse waves. We put the transverse wave in a coordinate system and we define it by the points, by vertical distance, by horizontal distance. Now we'll continue defining with longitudinal waves. Pumping a spring back and forth produces longitudinal waves. As you see, when you pump it forward, you produce a region of compression. Yani coils are getting tighter, compression. But between two tighter regions, there is a stretch region. Yes, this pumping a spring back and forth produces compressed and stretch regions. As you see, yes, stretch region, compressed region is moving. Then another compressed region is moving, but compressed region followed by a stretch region. These compressed regions, another compressed region, and between them is stretch region. These regions are regions of higher density. Because if the particles are get closer, density increases. Also pressure increases. But perhaps you know. So the coils of the spring are higher, they are closer in some regions. These are compressed regions. So these are regions of pressure, higher pressure and density. But between two compressed regions, there is a stretch region. Now in here, the coils are not so close. They are far, loose from each other. The coils of the spring are looser from in some regions. These regions are called stretch regions. And in these regions, because the particles are far from each other, density is low density, low pressure. Yani regions of low pressure and density are stretch regions. Then we can draw a waveform, but this waveform is going to describe how pressure and density is changing in the medium as a longitudinal wave travels. If here is the compressed region, then pressure and density is the highest as you see. And in another compression, another highest point. But between two compressions, lowest pressure and below the normal pressure. This line is normal pressure. So higher than normal, lower than normal, higher than normal, lower than normal. Which higher than normal represents, or highest than normal represents, compression. Lowest than the normal represents stretch region. And because the source is vibrating in simple harmonic motion, this waveform is also sine wave. Yani being sine wave is not about type of waves, it's about the source. If the wave source is vibrating, whatever this is, transverse or longitudinal, vibrating with simple harmonic motion, both transverse and longitudinal wave can form sine waves. Some students were asking that, because sine waves are longitudinal or transverse, both. It's about source. Source to be vibrating simple harmonic motion or not. Okay, in here, we consider that this, whatever the source is vibrating with simple harmonic motion. This one waveform is a sine wave. Okay. And crest of the sine wave is compression. Trough of the sine wave is stretch region. Okay, now define for a transverse pulse is this, as you see, it's traveling perpendicular to wave motion. It's a transverse pulse transverse. Periodic transverse is several pulses together. This force periodic transverse wave. But for a longitudinal wave, if you are going to talk about pulse, a pulse is going to be single compression. One compression or one stretch. One stretch is one pulse, one compression is also one pulse. But together they form a complete wave. One compression, one stretch. Or several compressions and stretches one after another. It's going to be periodic longitudinal. Label the following each graph. Where is crest, where is trough, where is wavelength, where is amplitude. About transverse wave, everybody knows it. We defined it, it's not going to talk. I will talk about the longitudinal line. So crest of the density wave corresponds to compression. compression is a crest. Rarefaction, trough of this fragile wave stretch region, etc. Another crest is another compression. Another trough, another stretch region. Yani crests corresponds to compressions, troughs corresponds to stretch regions. What about amplitude? Amplitude is from equilibrium position to a crest. Where is equilibrium position? Here, in the pressure wave. Corresponds to where? Right here. From equilibrium to a compression, it's an amplitude. Or from equilibrium to a stretch, also amplitude. What about wavelength? So what is the definition of the wavelength? From crest to crest. Or from trough to, or from compression to compression. From stretches into stretches also wavelength. And one thing I forgot to say, important. In longitudinal wave, the vertical axis is going to be density or
Displacement.
density or pressure, but in transverse, displacement. Then frequency. Frequency of the wave. Because the particles of the medium is vibrating in simple harmonic motion, we are going to define every quantity in simple harmonic motion can be defined for wave motion. Wave frequency. First, we should know that wave frequency only depends on the source. Bunu o kadar çok söyledim ki hala hata yapanlar var. İlk derste dedim ki only the source frequency determines the wave frequency. The vibration of the source is transferred to particles of the medium. And how many times the source is vibrating? Every particle in the medium vibrates with the same frequency. Even they travel from one medium to another, it doesn't matter. How many times the particles of the first medium vibrates? Second medium's particle also vibrates the same number. Frequency doesn't change for a traveling wave. Write it with a big letter. Frequency and period never changes for a traveling wave. Never. Just you can make a change by the source. If the source vibrates at a higher frequency, maybe it's a higher frequency. But after you do it, you cannot change it anymore. So frequency of the source determines equal to frequency of the wave. Also in chapter 4, section 2, remember, the strings frequency, standing waves, and sound frequency are same because they are, one of them is source, the other one is wave. Instrument frequency and sound from the instrument, same frequency. One of them is source, the other one is wave. So wave frequency describes number of crest or trough that passes a given point in a unit of time. Because we know that from crest to crest or from trough to trough, it is one wave. When we are counting the crest or trough, we are counting the waves. One crest to next crest, one wave passes. Another crest, one more wave passes. That's why second definition is about the number of waves. Describes the number of waves that passes any given point. Yeah, these two definitions are equivalent. Counting the number of crests means counting the number of waves. Counting the number of trough means counting the number of waves. And number of crests or trough, or number of complete waves, or number of vibrations, or number of oscillations, or number of cycles divided by total time, always equal to frequency. But period, time for one cycle, we did in the simple motion, time required for one complete vibration of the particles of the medium. We are particle of the medium must complete one cycle of vibration. Then time for that is period. And it's also defined as the time it takes for one complete wavelength to pass a given point. But how they are related? One complete wavelength forms by two half cycles, correct? One complete wavelength. Yani two half cycles, one complete cycle. When one complete vibration happens, wave travels one wavelength. Yani wave times are equal. Both are periods. Both are periods. And periods definition is total time divided by number of crests or troughs, or number of vibrations, number of waves. And relation between the period and frequency also same as in waves, just like simple harmonic motion. What was that? If you multiply them, the result is 1. So for a wave's frequency and period, if you multiply, the result is 1. A vibration frequency and period, multiply again, the result is 1. Then we can write two alternative version. T is equal to 1 over F, or F is equal to 1 over T. But speed of a wave depends on medium. Only medium, or change in property of the medium, not frequency. So speed of a mechanical wave is constant at a given medium at the same condition. Then if you want to change the speed of a wave, you have to transfer the wave from one medium to another, from air to water. It was the example I did in the test lab. From air to water, if the wave travels, what changes? Speed changes. Frequency, period, unchanged. Again, for a traveling wave, we cannot change frequency or period. It doesn't matter from which medium to which medium it moves. Only speed changes from medium to medium, or property of the medium, such as temperature. In chapter 4, we talk about this in details. And if calculating speed, because speed of the wave is constantly given medium, we are going to use classical speed calculation method. What is it? Distance traveled by an object divided by time for travel. Yani delta x over delta t. But this is common definition of speed. Why don't you write this in terms of the wave motion? How? Delta t, say that 1 period. In 1 period, a wave travels a distance which is equal to 1 lambda. In 1 period of time, nerede gördük onu? In here we saw. Look at that. Period is the time it takes for a complete wavelength to pass a given point. And in 1 period, a wave travels 1 lambda. A wave travels 1 lambda. So I'm going to write instead of delta x lambda, a time for lambda to pass from a given point is period lambda over period is the equation. And 1 over period is what? Frequency. Then we are going to write the equation for the wave. Lambda times frequency is speed of a wave. We are not going to calculate, but we will comment on this equation. This is several questions I asked about just about this. For any given medium, that if there is no change in the medium, no medium, same medium, what is constant? Is constant. In air, for example, when I was talking in this area, sound, my sound is same speed everywhere. But if V is constant in a given medium, lambda and F are inversely proportional. Yani, if you scream high frequency, wavelength gets shorter. Frequency higher, wavelength shorter. If you make a low pitch sound, this time frequency is lower, wavelength is longer. They're inversely proportional. So thus frequency and wavelength of a wave inversely proportional in a given medium. Speed of a wave is independent from that. What is dependent on this? For a wave traveling from one medium to another, from, for example, air to water. As wave travels from air to water, what happens? The speed changes, but frequency? Same F. Same F. Here is V1, small. Here is V2, big. So, in this case, lambdas must be also different, huh? If this is the same, these are different, these two must be different as well, even directly proportional. Yani as a wave is traveling from one medium to another, speed and wavelength directly proportional. Faster, longer wavelength. Slower, shorter wavelength. And energy. Wave transfers energy from one point to another. And energy transferred by the wave proportional to square of the amplitude. If amplitude doubles, energy increases by 4. If amplitude triples, energy increases by 9, square of that. Or if we want energy to triple, amplitude should increase by what? Let's do it.
By square.
Energy is a squared. If you want energy to increase by 3, to make it 3e, left side also must be 3e squared. This is change factor of what? A squared. If a squared is a change factor of 3, but we are looking for a, take the root. A is going to have a change factor, which is root of 3. Okay. Of course, no waves infinitely vibrates because of the mechanical energy of the vibration is converted to heat. Yes, this is called damping, just like the definition we give in simple harmonic motion. Because of the friction, vibration, mechanical energy decreases by time, and finally vibration stops. This effect is called damping. This is all about section 3. Let's continue section 4. And we are going to finish today with section. This is chapter 3. Chapter 3, section 4. In this section, the most important title is standing waves. Already you know, because we talked about standing waves in chapter 4, section 3 as well, when we are talking about the harmonics. Okay, first, interference. What is interference? If two objects meet each other, or two-way meet each other, this is called interference. Material objects, when they interfere, they cannot come across each other. But waves are not like this. Waves can occupy the same space, otherwise you could not listen to music. Waves are occupying the same, they are coming and then vibrating or eardrum at the same time, which makes the sound. So that's why we say that two bumper boats and metal objects cannot occupy the same space, but waves can do. This is what we are talking about. When two waves come across each other, they can, when they meet, they will pass through each other without any change. This interaction when two waves come across each other is called interference. Two types of interference we are going to observe. One of them is constructive. If the waves are vibrating, even though in your book this definition is given by displacement. When the book talks about displacement, they are talking about the direction of the vibration. Displacement from equilibrium position. If there is displacement from equilibrium position in the same direction, like positive phi and positive phi, these two waves constructively interfere. They support each other. One of them's amplitude say that 3 centimeter, the other one say that 2 centimeter resultant, 5 centimeter. Yani 3 plus. But later what happens? For an instant they overlap. Instead of two waves, you will see a single one waveform. But they pass through each other without change. Yani this 2 centimeter wave passes to the left, 2 centimeter waves to the right, they go on there without any change. It's like one wave cannot destroy another wave. Only for an instant, they combine and form a resultant waveform. But if the displacement directions are opposite, yani one wave is displacing positive y, the other one is negative y, this time they are going to interfere destructively. In this case, we are going to subtract the amplitudes. Yani if you say this is again 5 and 3, it's going to be 5 minus 3, the result is 2. And then again they will pass through each other without any change as original. They continue their path. And complete destructive interference happens if two waves displacement directions are opposite, positive phi and negative phi, and they are equal in magnitude, they will cancel completely each other. You cannot see any vibration for an instant, which is complete destructive interference. So interference happens for all types of waves, not only for mechanical waves. Also electromagnetic waves, chapter 7 we will study. Not only for transverse waves, these are transverse, also longitudinal longitudinal waves. But longitudinal waves interface is a little different. Compression and rarefaction, which is crest and trough. When they meet, destructive interface. But if compression crest, another compression, another crest, when they meet, constructive or rarefaction trough, another rarefaction trough, they also constructive interface. They make it rarefaction to rarefaction, which is the stretch region, or compression, they form constructive interference. One rarefaction, another compression meet, they form destructive interference. And reflection. So waves reflect. We are going to study reflection from fixed boundary and free boundary. So as pulse is sent to a fixed boundary, as you see, here is the fixed. A pulse is sent to a free boundary. As you see, there's a ring grid can vibrate up and down. When this pulse reaches to the fixed boundary, right here, like this position, it wants to vibrate this wall up. That's why it acts a force on the wall. But it's a wall. It's fixed. It doesn't move. That's why this action force on the wall gives a reaction on the rock and causes this rock to be inverted. Reaction force by the wall. That's why from the fixed boundary, a wave is reflected and also inverted. But in free boundary, because this rock is free to vibrate, no force acts on the wall. No force acts on the wall, no reaction, no action, no reaction. That's why only reflection. No. That's why it was the quiz question. Huh? So, from the free boundary, it is reflected but not inverted. And standing waves. This is a model for standing waves. Standing waves are formed by two waves which pass through a medium opposite directions. One of them is moving from right, left to right, the other one is moving from right to left. Then, instead of seeing these two waves, you are going to see just single waveform, which is interference of these two waves, which seems to be only vibrating up and down, but not traveling. But look at the component waves. One of them is moving from left to right, the other one is from right to, and component waves are moving. Resultant wave pattern is not moving. Standing wave is not moving back and forth. Wave A, wave B, they are trapping, but we don't see them. We see here superposition, interference. This one seems to vibrate. But this happens only if the waves have the same frequency, same wavelength, same amplitude. It happens. And also they don't happen at every frequency. At some certain frequencies they form, at some certain wavelength they form. Yes, the waves moving towards the fixed end and the waves reflected from the fixed end overlap, meet each other and interfere, constructive and destructive at different regions of the string, and standing wave forms. When we check this, we are going to see that some points never vibrate. These points which do not vibrate, called nodes. Why they don't vibrate? Why their net displacement is zero? Because if you check very carefully, these two waves always destructively interfere here. If I stop this simulation, but I cannot because there is no such a notion, you are going to see that addition of the displacement of these two waves are zero always. In here zero, in here zero, in here zero, in here zero, they are nodes. But at this point, wave vibrates with the largest amplitude. This point is called antinodes. As you see, from one antinode, one node to the next node, there is an antinode. Between two antinodes, there is a node. These are the patterns. First order standing wave forms at the lowest frequency, longest wavelength. When the glass shot, I shake my hand at the smallest frequency. And we form this. one loop. This shape is called a loop. How many nodes?
2
Entire nodes. How many antinodes? One antinode. Yani first order standing wave. One antinode, one loop, first order. But second pattern, 1, 2, 3 nodes, but 2 and 2 loops. So that's why we said that fixed, because entire nodes, node is one greater than antinodes. These are the patterns. First order standing wave, second order standing wave, third order standing wave, fourth order standing wave, first order standing wave, because ends are fixed, one loop. Second order, 2 loops. Third order, 3 loops, goes on this way. Fourth order, 4 loops. Number of loops and order of standing waves are same. 1, 2, and is equal to 2. 1, 2, 3, and is equal to 3. Orders. These are the orders. And distance between 2 successive node and 2 successive antinode is lambda over 2. Why? Because it seems to be like a pulse, huh? Like a pulse. A pulse is half of a wave. Wave has a 1 lambda. O zaman pulse half lambda. That's why this is half lambda. From node to node, half lambda. From node to node, half lambda. But from antinode to antinode, again half lambda. Half of half plus half of half, it's half. Half over 2 plus half over 2. Yani 1 over 4. Now, by the time, this is also important. From antinode to node, 1 over 4. Lambda over 4, yeah. From antinode to node, lambda over 4. And from antinode to antinode, lambda over 4 plus lambda over 4, lambda over 2. O yüzden we should know this. From node to node, antinode to antinode, what is distance? Lambda over 2. But from node to antinode, or antinode to node, it is lambda over 4. And as I said, the standing wave patterns occurs not at every wavelength, not at every frequency. They form at some specific wavelength. By this equation, we can find at what wavelength this standing wave forms. L, length of the string. N, order of the standing wave. N is equal to 1, 2, 3, 4. So lambda is the wavelength which produces this pattern. For example, as such string fixed at both ends, which is length equal to 2 meters. What are 3 wavelengths which will produce standing waves on the string? Yani, find lambda 1 which produces standing wave, find lambda 2 which produces standing wave, find lambda 3 which produces third order standing wave. Use equation. Which equation? Lambda is equal to 2L over N. Lambda 1. I have tried in here 1 and 1. Do you remember this from harmonics? Fundamental wavelength, huh? Fixed. String instrument fixed at both ends. Fundamental wavelength is 2L. Fundamental frequency, V divided by 2L. We did flip this number. So how much is L given? 2 times 2? Next harmonic, lambda 2. 2L over 2. It is L. How much? What happened to the wavelength?
Decreases.
Even half, huh? Do you remember again harmonics? Fundamental frequency lambda 1, second harmonic lambda 1 over 2, third harmonic lambda 1 over 3. So it goes the same way. Lambda 3, 2L over 3. Insert number 2 times 2 divided by 3. Result is going to be 1.33. These are the wavelengths which produce a standing wave, and remember the pattern. Pattern of the first harmonic was like this. 1 loop. Second harmonic, 2 loops. Third harmonic, 3 loops. These are the wavelengths which produce a standing wave. Yani no other numbers can form these patterns. It says name at least one wavelength they will not produce. Tell me a number between 4 and 2. 3.5, 3.1, 3. Any number between 4 and 2 cannot. Any number between 2 and 1.3 cannot. One more thing, in the test you can use this. Lambda is equal to 2L over n, correct? In the multiple choices you can find if a wavelength can produce a standing wave or not by writing n is equal to 2L over. If this division is an integer, that wavelength produces a standing wave. Integer, like 1, 2, 3, 4, 5, 6. We did this in some questions. And they are going to give you choices to you. For example, if choice A is 4, choice B is 2 for this question. I can understand if they produce standing wave or not by using this. How? N is equal to 2L. L is how much? 2 times? Divided by, what is lambda in choice A? Divide them, is the integer? Divide them, is the integer? No, not meter, of course. 1. First order standing wave, yes it is. So 2. N is equal to 2 times 2 over 2. Is it what? Second order, it's an integer, it produces. Give a number between them. For example, 4 and 2, 3. Give 3. Let's check 3 produces standing wave or not. N is equal to 2 times 2 divided by 3. Is that integer? No. N must be integer. 1, 2, 3, 4. Otherwise, that wavelength cannot produce a standing wave. 1.33 is not integer. That's why this wavelength, 3 meter wavelength, cannot produce a standing wave. A wave with 3 meter wavelength cannot produce a standing wave because n is 1.3. It's impossible. N must be integer.